Welcome back, ladies and gentlemen. We're going to start chapter 12 today with section 12.1. It's all about three-dimensional solids today. Up on the screen, you'll see your exit question as always. And before you get into this video, I would highly recommend grabbing both note guides for chapter 12 because there is a ton of vocabulary and tons of new words coming at you in this particular segment. There's very little math to do, but there's a ton of vocabulary. Onwards we go. First definition, and the most important one, is polyhedron, or the plural version, polyhedra, is simply a solid that is bound by polygons. Now, bound means that there's no gaps, and polygons, we spent a whole bunch of time defining that earlier. Now, there are several types of solids that aren't polyhedra, so there are the cylinders, cones, spheres, and anything that contains any sort of curve or non-polygon face. Next up, we have many different types of polyhedra. First, prisms and pyramids. Okay, prisms differentiate themselves from pyramids in that they have all parallel sides. They have two congruent bases and then parallel sides that connect the two parallel bases. Okay, they can be askew. They don't necessarily have to be perpendicular to their base. They can be tilted over, but they will be named for their base and then just follow it with the word prism. So you identify the base, say a pentagon, you call it a pentagonal prism. Likewise, the naming of a pyramid is pretty much the same thing, the difference being that a pyramid comes to one point, or once you have a base, then all the other faces converge into a single vertex. And it again is named after its base. So if you have a hexagonal base, you say it's a hexagonal pyramid. On to more interesting things. These are the only 5 Platonic solids, and that was actually named after a dude named Plato. He came across these three-dimensional shapes. These are the only 5 three-dimensional shapes that fit this strict set of rules. A convex polyhedron composed entirely of one type of regular polygon with the same number of faces meeting at each vertex. So if you look at each vertex, there's 3 faces meeting it. This vertex, there's 3 faces meeting it. This vertex, there's 1, 2, 3, 4, 5 faces meeting there. These particular shapes have, at least a couple of them, have very real applications in terms of atomic structure, particularly the first one. If you look at tetrahedrons, that is the building block of nature right there. That is a 109.5 degree angle, and that is what carbon likes doing. So the backbone of every piece of biological life is carbon, and it structures itself and it bonds to other molecules. So this central atom is carbon, and the surrounding atoms bond in a tetrahedral pattern most of the time. At least that's what carbon is most comfortable doing. There's also silicon that bonds the exact same way, another highly prevalent molecule or element in the Earth's composition, and it has the same bonding structure as this, as do a couple elements that are highly present in your body, phosphorus and nitrogen. Even though they don't have the exact same bond structure, they have the same bonding geometry usually. So they will form, they like that 109.5 degree angle. Some of these are fairly exotic. The icosahedron, this is what steel or a lot of crystalline structures, a lot of metal alloys look like. So in this picture, this is an aluminum alloy with a central atom that's providing some structure to the aluminum. So it creates a much stronger alloy of aluminum than if there were just these blobs of aluminum atoms floating around without that crystalline structure. Here's a favorite, dodecahedron. You'll notice that the degrees here are, I think they're 108 degrees, which is super close to that 109.5 that carbon loves. So this is actually a very easy molecule to synthesize. This is kind of exotic. Some molecules bond with 6 neighbors in an octahedron pattern. And this one is basically possible, but it doesn't last very long because you'll see those carbon atoms or those atoms at the corners are basically making a 90-degree angle with some other ones, and that's very far away from that 1095 bonding angle that carbon likes so much. So that one will explode, but all of these other ones are very, very stable and they occur very frequently. And they're based on the geometry of these Platonic solids for the most part, with the exception of the cube. Then if you take a Platonic solid and chop off some of its corners, you will often end up with what's called an Archimedean solid, which is an Archimedean solid is a solid that is composed of two or more regular polygons. So the faces of it are all still regular polygons, but there's a mixture of octagons and triangles, or squares and triangles, or hexagons and squares and, all that stuff. So I would challenge you to try pronouncing some of these solids names. You don't need to know very much about these other than they exist, and there's lots of ways to make solids, particularly, say, a soccer ball, which is, I think, on here somewhere. There it is. Truncated icosahedron. There you go. That's a soccer ball. Next, parts of solids. You need to know what a base is. You need to know what a face is. You need to know what a vertex is. And you need to know what an edge is. And you need to be able to count them all for any given solid. So first off, the base, if we're talking about a prism, it is the two parallel sides to each other that are not rectangles. So in this case, the pentagon. Notice that every other face of this prism is a rectangle. If it's a pyramid, we're talking about the one that all the triangle flaps fold upwards and go to a point to. And sometimes the base might not be so obvious, and sometimes you might have a choice as to what to call the base, like in a cube or a square prism of some sort. So you might have some leniency there in terms of what to call the base. A face of a solid is simply the polygon that makes up that solid. The edge of a solid is where two faces intersect, and the vertex is the point where three faces intersect. Euler's theorem, that is pronounced Euler, and he came up with this theorem. It's theorem 12.1. You're not going to use it very often, but you might get a problem or two asking about it, which simply states that the number of faces of a solid plus the number of vertices in a solid is equal to the number of edges in a solid plus 2. So you can do that for any polyhedron. Next, a couple of vocab words again. Regular polyhedron, all faces are congruent. So this doesn't restrict itself to the same number of faces intersecting at a vertex. So that creates a whole new class of polyhedra in addition to the Platonic solids. Convex polyhedron, very similar to a convex polygon, where if you connect any 2 points in or on the solid with a segment, that segment will be contained entirely within the solid. Conversely, or the opposite of that would be concave polyhedron, where you can draw at least one segment where there's some daylight showing between the shape and the line that was drawn between 2 points. Cross sections. Here's a cube. We sliced it with a plane. You need to be good at identifying what shape it would make. So why don't you pause the video and see if you can identify the 4 shapes that result from slicing a cube in certain ways. There are the answers. This is a square. We know this is a cube, so this cross-section is a square. Again, here you get 2 sets of parallel sides and 4 right angles, so that's a rectangle. Here's a trapezoid, and this is a triangle. The assignment this time is out of the workbook. I'll see you next time.